Heat is the invisible constraint inside every electrolyzer. When we talk about hydrogen production, we focus on voltage, efficiency, stack cost, degradation, and electricity price. But underneath all of that, there is a continuous thermal load that never stops. Every second the electrolyzer runs, it produces heat. And if that heat is not removed correctly, performance declines, materials degrade, and the entire plant economics shift. So today we are going to break down the heat transfer problem inside electrolyzer cooling systems, step by step, from cell physics all the way to a 50 megawatt plant in a desert climate. And we will do it visually, referencing each diagram as we move. Let's begin with image number 1. In image number 1, you see a PEM electrolyzer cell cross-section. Hydrogen evolves at the cathode, oxygen at the anode, separated by the membrane. Now focus on the voltage numbers overlaid on the image. The thermoneutral voltage for water electrolysis is 1.481 volts. That is the voltage at which the electrochemical reaction neither absorbs nor releases heat overall. But real systems do not operate at 1.481 volts. They operate at higher voltages due to activation losses, ohmic resistance, and mass transport limitations. Suppose the cell operates at 2.0 volts. The difference between 2.0 and 1.481 volts does not go into hydrogen production. That difference becomes heat. The heat generation per cell is calculated using the equation shown on image number 1. Q equals current, multiplied by the difference between operating voltage and thermoneutral voltage. Now apply real numbers. If the current is 2,000 amperes and the voltage difference is 0.519 volts, the heat generation per cell is 1,038 watts. That is just over 1 kilowatt of thermal energy per cell. And that is not a transient load, it is continuous. Now scale that to a stack. Move to image number 2. In image number 2, we zoom out to a 100 cell stack. Each cell produces approximately 1,038 watts of heat. Multiply that by 100 cells and you get 103.8 kilowatts of thermal load. That is the heat that must be removed just to maintain steady-state operation. Notice something important here. The heat is distributed across the stack. It is not concentrated in one location. That means your cooling system must remove heat uniformly. If one section runs hotter than another, you get uneven membrane degradation. You get localized stress, you shorten stack lifetime. Now let's quantify the cooling requirement. Move to image number 3. Image number 3 shows the coolant loop and the governing equation for temperature rise. The temperature increase of the coolant as it flows through the stack is equal to the heat load divided by the mass flow rate, multiplied by the specific heat capacity. For deionized water, the specific heat capacity is approximately 4.18 kilojoules per kilogram per Kelvin. We rearrange the equation to solve for required mass flow rate. If the stack generates 103.8 kilowatts of heat, and we allow a maximum coolant temperature rise of 10 degrees Celsius, the required mass flow rate becomes 2.48 kilograms per second. That is about 148.8 liters per minute. Now pause and think about that. If you decide that 10 degrees is too much variation and you want tighter thermal control, say 5 degrees, your required flow rate doubles. That means larger pumps, higher pressure drop, thicker piping, and more parasitic electricity consumption. Cooling design is always a trade-off between thermal uniformity and energy efficiency. Now let's scale this to industrial level. Move to image number 4. Image number 4 shows a 50 megawatt electrolyzer plant. From earlier energy balance calculations, we know that approximately 17.7 megawatts of electrical input ends up as thermal waste that must be rejected. That is 70.7 million watts of continuous heat. That is equivalent to thousands of residential air conditioning systems operating simultaneously. This is where cooling stops being a minor subsystem and becomes infrastructure. Now climate enters the equation. Move to image number 5. Image number 5 shows a dry cooling system operating in a desert environment. Let's assume we are designing a plant in Abu Dhabi with a design ambient temperature of 50 degrees Celsius. Air-cooled systems reject heat to the ambient dry bulb temperature. But they cannot cool the water below that temperature. In fact, they require an approach temperature difference. Assume 12 degrees Celsius approach. That means the coolant return temperature cannot be lower than 62 degrees Celsius. If the stack outlet temperature is 75 degrees Celsius, then the available temperature difference for stack cooling is only 13 degrees Celsius. Now apply the equation. To remove 17.7 megawatts with a 13-degree temperature rise, you need a mass flow rate of 325.7 kilograms per second. That is nearly 19,540 liters per minute of coolant flow. Next, calculate required heat exchanger surface area. Using a conservative overall heat transfer coefficient of 30 watts per square meter per Kelvin and a log mean temperature difference of 15 degrees Celsius, the required area becomes 39,333 square meters. That is enormous. And fan power, approximately 2% of the heat load. That equals 354 kilowatts of continuous electrical consumption just to move air across the heat exchanger surface. Dry cooling has zero water consumption, which is valuable in desert regions, but it requires massive surface area and significant parasitic power. Now let's compare with wet cooling. Move to image number 6. Image number 6 shows an evaporative cooling tower. Wet cooling leverages evaporation, which allows water to cool toward the wet bulb temperature rather than the dry bulb temperature. If the design wet bulb temperature is 30 degrees Celsius and the tower achieves a 5-degree approach, then coolant return temperature becomes 35 degrees Celsius. Now the available temperature difference across the stack is 40 degrees Celsius instead of 13 degrees. Apply the same heat balance. To remove 17.7 megawatts with a 40-degree temperature rise, the required mass flow rate drops to 105.9 kilograms per second, or about 6,854 liters per minute. That is less than 1/3 of the dry cooling flow rate. Thermally, wet cooling is far more efficient. But now calculate water evaporation. Using a typical evaporation rate of 1.5 liters per kilowatt hour of heat rejected, the plant loses approximately 26,550 liters per hour. That equals 637 cubic meters per day. Now compare that to electrolysis water consumption for hydrogen production, approximately 327 cubic meters per day. Cooling consumes nearly twice as much water as the hydrogen reaction itself, in an arid region that changes the entire water balance of the plant. Now let's integrate the system components. Move to image number 7. Image number 7 shows the full electrolyzer cooling circuit. Deionized water circulates through the stack in a closed loop. The hot coolant exits the stack at around 75 degrees Celsius. It flows into a plate heat exchanger. On the secondary side, cooling tower water absorbs the heat. The cooled DI water returns to the stack at approximately 60 degrees Celsius. A circulation pump maintains flow. An expansion vessel accommodates thermal expansion. Temperature sensors maintain control within plus or minus 2 degrees Celsius. That tight control band is critical for membrane longevity. Optionally, waste heat recovery can extract usable thermal energy. Up to 2 megawatts from a 10 megawatt module may be recovered for district heating or absorption chilling. In colder climates, this improves overall system efficiency. Now examine the cooling technology performance envelope. Move to image number 8. Image number 8 plots cooling capacity versus ambient temperature for dry, wet, and hybrid systems. Dry cooling performance declines as ambient temperature rises. Above 50 degrees Celsius, thermal margin becomes extremely narrow. Wet cooling maintains capacity because evaporation depends on wet bulb temperature rather than dry bulb temperature. Hybrid systems operate dry under moderate conditions and switch to wet assistance during peak heat. This is not a theoretical curve. It defines operational feasibility. If a plant derates hydrogen production during peak summer conditions, revenue drops precisely when electricity prices may be volatile. Cooling design directly affects plant revenue stability. Now step back and interpret what we have learned. Heat generation inside electrolyzers is dictated by electrochemistry. It scales with current and overpotential. Cooling requirements scale with stack size and plant capacity. Ambient conditions constrain heat rejection. Water availability constrains cooling technology choice. In hot climates, dry cooling reduces water use but demands enormous surface area and fan power. Wet cooling reduces surface area and flow rate but consumes vast amounts of water. Hybrid systems balance annual optimization but increase complexity. Cooling design therefore impacts capital cost, operating cost, parasitic load, water demand, and stack lifetime. It is not a secondary engineering discipline. It is central to hydrogen plant feasibility. When designing an electrolyzer cooling system, engineers must evaluate worst-case ambient temperature, wet bulb temperature, allowable stack temperature rise, pump energy, water sourcing, scaling risk, and regulatory constraints. The system must be designed for extreme design day conditions, not average annual temperature. If you ignore that, your plant may meet nameplate capacity on paper, but fail during peak summer heat. That is the difference between theoretical hydrogen production and bankable hydrogen infrastructure. And here is the deeper insight. Hydrogen plants in hot desert regions face a structural tension between electricity and water. Dry cooling increases electricity consumption through fan power. Wet cooling increases water consumption through evaporation. In some cases, desalination energy required to supply cooling water may exceed the parasitic fan power of dry systems. So cooling becomes an optimization problem across multiple resource constraints. Electrochemistry determines how much heat you generate. Climate determines how easily you can reject it. Water availability determines which technology you can deploy. Heat transfer is not just a physics equation, it is a site-specific infrastructure decision. And at scale, it determines whether hydrogen production remains technically and economically viable. That is why serious hydrogen developers analyze cooling systems at the feasibility stage, not after stack procurement. Because once the stack is specified, your operating temperature window is fixed. Your cooling architecture must adapt to that constraint. And if you miscalculate, your plant may operate, but it will operate stressed. In hydrogen engineering, temperature control is durability control. Durability control is capital preservation. And capital preservation is bankability. So when you see a 50 megawatt hydrogen plant, do not just look at the electrolyzer stacks. Look at the cooling towers, look at the heat exchangers, look at the pumps. Because hidden behind the hydrogen production numbers is a continuous thermal battle that must be won every second the plant runs. That is the engineering reality of heat transfer in electrolyzer cooling systems. And that reality scales from a single cell generating 1 kilowatt of heat all the way to a megawatt scale industrial facility operating in extreme climate conditions.